All right, hello everyone. So today we're going to have a look at proof by induction. And it's probably the most popular way of proving things. It's used throughout maths. Now it has a couple of, like everything else, it has its detractors. The main detractor is it proves using integers. Okay, so and usually the sums that we're dealing with, require that an integer be submitted in for a value, a variable. So you'll see as we go along. I like this because it's a nice. You can have fun with this one as opposed to some of the other ones. So imagine a sequence of numbers: 1 plus 2 plus 3 plus 4 plus n. So, in other words, the sum of all the natural numbers. Okay? And imagine that when you add up the sum of the first n natural numbers, you can display it or you can predict it using a formula like this. Okay? This is a famous formula. You'll find it in a lot of maths books. It's Euler's method for adding the sum of n natural numbers. Basically, if I want the sum of the first four natural numbers, I put in 4 over 2, bracket 4 plus 1, close bracket, and I'll get the sum. Simple as that. And obviously, the sum of the first four natural numbers, you can add it up yourself, it's 10. So 4 over 2 times 4 plus 1, 4 over 2 is 2, 2 times 5 is 10. So it does work, okay? So how do we prove this, okay? Right, for absolutely every proof by induction, you'll do the first three steps exactly the same way. It'll only be the final step that will vary depending on which type you're doing, okay? So for these standard formulaic types, okay, where you have a formula that's stated for you, okay, I'm going to show you the simplest one. So step one, okay, prove it's true for n equals 1 for the first natural number, and obviously n an element of the natural numbers. Okay, so let's prove it's true. Okay, so if n is 1, then 1 should be equal to 1 over 2 times 1 plus 1, and that's true. 1 is equal to a half of 2. That's true. Okay, so I'm going to step 2. I'm going to assume it's true for n equal to k. Okay, and k, an element, the natural numbers. So let's sub it in. So if it's true, I'm going to put in k is equal to k over 2, bracket, instead of n plus 1, k plus 1. So there's my assumption that for any value of n I put in, it's going to, for any value of n I put in this case k over 2 times k plus 1 should be the sum of all the values up to k. Okay, so 1 the whole way up to k. Now, step 3. Based on step 2, so these are always going to be the same no matter what. Based on step 2, we're going to show it's true for n equal to k plus 1. In other words, not k, but the one after k. Okay, just like it wouldn't be n, it'd be the one after n. So instead of me proving it for 4, I'd be providing proof for 4 plus 1. In other words, prove it's true for 5. So how would I do that? Well, let's do the same thing. Instead of k, I'm putting in k plus 1 equal to, and instead of, excuse me, putting in k plus 1, so I'm going to pop it in to the formula. K plus 1 over 2 on k plus 1 plus 1, because there's already a 1 in there. So let's tidy this up. So that's k plus 1 is equal to k plus 1 over 2 on k plus 2. So that's what we're going to prove, that if I can put in a value of k, it should come out like this. And if I put in a value of k plus 1, in other words, the next value after k, it should turn out like this. Okay? Now, how do we prove it? Well, It's very simple. If you think you don't have to, this line I'm going to write, you don't have to write yourself. I'm just going to show you why, and then you can skip this line and just do the next thing. Okay, if you think about it, we've got 1 plus 2 plus 3 plus 4 plus k plus 1. Okay, so we're saying that all of that is going to be equal to this. Okay, but we already know what all of that it is. In other words, we know all of that is already this. So we're really saying that k over 2 times k plus 1 plus k plus 1 is equal to this new thing, k plus 1 over 2 on k plus 2. So in other words, we're saying that the step 2 that we've defined plus the next one over, there's the step 2, there's the next one over, the two of them together should be equal to what we've defined as k plus 1 based on our original algorithm. So let's see, are these two sides equal? Okay, so again, a couple of ways of doing this. Look, that's just k on k plus 1 over 2 plus k plus 1 equal to k plus 1 over 2 on k plus 2. So let's see, are these two sides equal? And if they are, well then it must be true. So how do I get to this common denominator here? On this side would be 2. So we'd have k on k plus 1 plus 2 on k plus 1 equal to that common denominator here would be 2. That'd be k plus 1 k plus 1 plus 2 on k plus 1. Okay. Sorry, that's a multiplication. So scrap that. You don't need to have to do that. So that side's a multiplication. So there's no plus between them. So I can just multiply those two. That's just k plus 1 times k plus 2 over 2. They don't look the same, but I see grouping here. And if you remember from junior cert, you can just take the outside factors, take the inside factors, and they're the same. So, what does that mean? Well, this is how you finish it off. If you've proved that the two of them are the same, in other words, if you've proved that the k plus 1 version is the same as the k version plus k plus 1, then what you're saying, if it's true for k plus 1, so if it's true for k plus 1, then it's true for k by assumption. Therefore, if it's true for n equals 1, it's true for n equals 2, etc. So there's your proof. Okay, so you have to make sure you put that in. If you've proved the truth for k plus 1, it must be true for k. And if it's true for n equals 1, it must be true for n equals 1 plus 1, which would be 2. So you're kind of going backwards to your assumption and then forwards from what you know to be true. Because I know this to be true. It is 100% true. But I can't be sure that the next one is true. But I made the assumption that if it was true for n equals k, n equals 1, it was true for n equals k, any value. And then I proved that it's true for the next one after k. And if it's true for the next one after k, it must have been true for the one before, which is k. And obviously, if it's true for 1, it must be true for the next one after 1, which would be 2 and 3 and 4. So there's your proof. It's a lot of this you don't need. I only put that bit in just to show you what you're doing. You're taking the bit you've declared in step 2, adding it to the k plus 1 from step 3 and making it equal to what you created in step 3. So there's your kind of circular logic on it. Okay, so we'll try another one soon.